Welcome to the course of mathematical method. And in this course, we have the chapters within involving the special functions, and also we have the Laplace transform and relativity. So first module is Laplace transformation and Laplace transform. So in this module, we will discuss about the basic ideas about the Laplace transform and its used to solve the differential equation. So Laplace transform or Laplace transformation is an important tool to solve many mathematical and physical problems involving ordinary partial derivative with constant coefficients or variable coefficients with suitable conditions, initial and boundary conditions. So in this chapter, we are going to learn following topics: basic formulas and theorems of Laplace transform, and solution of ordinary and partial derivative equation using LT. LT here is the short form of Laplace transform. Now, in the second section for this, we learn about the basic formulas and the theorems of Laplace transform. And this section is divided in several subsections. So the first subsection is the definitions and exercise of Laplace transform. So first we define what is Laplace transform, and Laplace transform of function f defined for t greater than equal 0 denoted by LFT is given by the integration fs is equal to ft 0 to infinity e to the power minus st ft dt. Provide the integration exists. Now we have the inverse Laplace transform. So the original constant f is known as inverse Laplace transform, noted by L inverse f s. Next, to discuss the existence of the Laplace transform, we introduce this concept about the exponential order alpha. So a function f is said to be of exponential order alpha if there exists constant alpha and m greater than 0, such that absolute value of ft less than equal n e to the power alpha t for t greater than equal 0. So there exists some alpha and n such that this inequality hold. So our target will be to find that n and alpha. It's geometrically the meaning for the exponential of order for alpha is that the graph of this function does not grow faster than the graph of the exponential function. This off. So that means the graph of this one will be on the above the graph of the function f. So we'll discuss it by the example. So let's take f1t equal to. So in this case, m equal 1 and alpha equal 1. And if we see the graph, so this is the exponential function. Hence, gt is equal to the power t, and this is the f1t equal t. Next example is f2t is equal to the power minus 2t. This is m equal 1, alpha equal 1. This so holds. And the graph of this function is, again, here this is exponential function, and this is exponential minus 2. And since we take a small range, so it is looking like a straight line, but it's actually not a straight line. Now we have third example. We have cosine t and n equal 1 and alpha equal 1. Yeah. So again here the graph is this for exponential and this is for cosine t. So cosine t is an wave kind of form, but here as we see that this is just going down straight line, but it is not exactly straight line. We take the range is from 0 to 3. That's why it is looking like that. So at 0, you can say this is 1. So at 0, they are matching on that point. But other than that, when it is increasing, the cosine t is going down and exponential is going up. So therefore, it is exponential order function. So now from this, we have the existence of Laplace transform. The necessary conditions is that if f is piecewise continuous, so there is need not be continuous. It is enough to have a piecewise continuous. Okay, here it's something strict. So price wise not is piecewise. Function on 0 to infinity and is of exponential order alpha for t greater than equal 0, then LFT equal Fs exists for s greater than equal r. So this is the existence for the Laplace transform. Now, one of the important property about the next section is linearity of linear transform, Laplace transform. So here we have this theorem, linearity principle, that if f and g two functions having Laplace transform, then for two constant a and b, LAFT plus BGT is equal. A constant will come out and then Laplace of ft plus b Laplace of gt. So we have a proof of this. So from the definition of Laplace transform, let's recall the definition, and ft equals 0 to infinity e to the power minus st ft it provided this integration exists. So this is the definition of the Laplace transform. Now ft will replace by this aft plus bgt, and then we'll have laft plus bgt equals 0 to infinity e to the minus st aft plus bgt from this definition directly. Now, since integrations, the constant can take out and we can separate the addition part. So we can rewrite it like this, e to the power minus st aft dt plus 0 to infinity e to the power minus st means dt. Then the constant a will go out. Then we have 0 to infinity to minus st ft dt plus b 0 to infinity to the power minus st dt. Now this one is the from this definition, if you see that this is the Laplace transform of f, and same way this is the Laplace transform of g. So therefore, it is a l f t, and this is plus b l g t. So this is the establish the linear property of the Laplace transform. And let's complete the first two subsection of it. Now in the next lecture, we have the Laplace transform of known